Now guys, let us start GM of FET. What is GM? Transconductance. Output current by input voltage. What is the difference between the conductance and transconductance? Conductance is current by voltage only, but either at input side or output side. That means ID by VDS, output conductance. Whereas ID by input current by input voltage, that is also conductance, input conductance. But guys, remember, output current by input voltage obviously represented by the letter GM, that is transconductance. Got it? Now the basic definition for FET is output current is drain current, so ID, and the input voltage in FET is VGS, so VGS. Guys, here GM is equals to dou ID by dou VGS. Yes, this is what the transconductance. And now what are the formulas in JFET GM transconductance? Guys, hope you know the drain current equation ID is equals to IDSS into 1 minus VGS by VP whole square. Yes guys, this is the drain current equation where ID is equals to IDSS into 1 minus VGS by VP whole square. Now what to do? If you want to get the GM from this equation, the best thing is you differentiate with respect to VGS, so that ID by VGS you will get GM only. Hence guys, we are differentiating the above equation with respect to VGS. Got it? So guys, here dou ID by dou VGS, which is GM only, that is equals to, now if you differentiate with respect to VGS guys, you get IDSS, differentiation of x square 2x, 2 into 1 minus VGS by VP, again differentiation of x, that is minus 1 by VP. This one guys, that is 2 IDSS into 1 minus 1 by Vp into 1 minus VGS by Vp. You can write easily guys like this, 2 IDSS by Vp into 1 minus VGS by Vp. This one guys, see this, you can remove this minus and you can keep here guys, mod Vp, and you can remove this. Yes guys, this is GM. So the expression can be written in such a way that it includes GM naught, where GM naught is maximum transconductance, or it is the transconductance at VGS is equals to 0. Because guys, whenever VGS is equals to 0, definitely you will get the maximum current. Whenever you get the maximum current, that could be the transconductance, that could be the maximum transconductance. That's it. So guys, here GM naught is the GM at VGS is equals to 0 or maximum transconductance. If it is GM, that is transconductance at VGS is not equals to 0 guys. This is what GM naught. Now you see guys, here the GM naught will be the maximum value, because there only you get maximum current, remember. So here GM naught is greater than GM. This is very important for the PSUs, remember, whether they may ask you to calculate the maximum transconductance, or they may ask you to calculate the transconductance for a given VGS, or else they may ask you any VGS or VP by giving VGM, by giving GM and GM naught. But the fact is, remember guys, GM is smaller than GM naught or GM naught greater than GM, remember. Now the point guys, here the same GM can also be expressed in another way. Let me do this. GM is equals to 2 IDSS by mod VP, which is a GM naught. Let me do this, 2 IDSS by mod VP into 1 minus VGS by VP. Guys, the same expression, let us take the drain current ID, that is IDSS into 1 minus VGS by VP whole square. Now guys, you move the terms, ID by IDSS under root, you will get it as 1 minus VGS by VP, and again you move the terms, VGS by VP. Guys, here this is 1 minus square root of ID by IDSS. Now you like here you can move this VP into that side, you will get VGS as VP into 1 minus square root of, let me do this guys, ID by IDSS. Okay, this is the VGS equation, input voltage equation of a JFET. Most of the people know only the drain current equation, which is this. Of course, this is very important, but see, what is the voltage equation VGS? You need to know, that is VP into 1 minus square root of ID by IDSS, that's it. Now guys, see, here 1 minus VGS VP is there, here also 1 minus VGS VP is there. Why don't you substitute here, so that 2 IDSS by mod VP into square root of ID by IDSS, this one guys. So you can rewrite it as 2 by mod VP square root of ID IDSS. That means guys, GM has one more formula, 2 by mod VP square root of ID IDSS. Now guys, here you see this formula. What is transconductance GM? It is directly proportional to ID. What is ID? Of course it is ID only, because drain current transconductance is directly proportional, right? See here. But exactly GM is directly proportional to square root of ID. This is very important for PSUs. Now the question may ask like this, the transconductance of a JFET is directly proportional to ID, ID square, square root of ID, ID cube. Actually it is directly proportional, but exactly speaking it is square root of ID. Okay, so GM is directly proportional to square root of ID guys. This is what the transconductance of FET. Hence we can give in a summary way, GM is GM naught into 1 minus VGS by VP, where GM naught is 2 IDSS by mod VP. Similarly guys, GM is equals to 2 by mod VP square root of ID IDSS. This is also another formula. Guys, you want to know the important relationship. Why JFET doesn't have any thermal runaway? Why only like BJT has thermal runaway? Because BJT is a NTC device. Whenever temperature increases, the reverse saturation current increases, IC not, so that IC increases, so that there is a more heat which destroys the transistor after some iterations, some cycles. That is what thermal runaway. Being it is a NTC device, thermal runaway will happen. Any device, if it is a NTC device, thermal runaway will happen. Whereas guys, JFET, thermal runaway is not there, don't worry, thermal runaway is not there. How? Because guys, as the JFET construction, as you are considering only the majority carriers, there is no question regarding the minority carriers, remember. So forget about the leakage current sensitivity, leave it. Moreover, whenever temperature increases, in FET channel, among the charge carriers there will be collisions. Because of the collisions, the mobility decreases. If mobility decreases, definitely current reduces. If current reduces, drain resistance increases. So guys, we can say clearly, as temperature increases, collisions occurs. Because of the collisions, definitely mobility decreases, therefore drain current reduces, hence drain resistance increases. So guys, this is enough, no need write any sentences. We don't tell you in the sentences. Remember guys, in SpaceGate Engineering Academy, we teach in such a way that you don't require bundles of pages, so many books, not required. We will teach you in an optimized way. Remember, we will teach you in an optimized way, like this. Like in shortcuts ways, if you want calculator for that particular problem, don't worry, without problem how to solve it, we will tell you. Just trust us and join us. Register for our course, definitely you will get benefit. No need to refer so many websites, YouTube channels, books, materials, institute materials, not required if you register for our course. Got it? Now let us see here, as temperature increases, drain resistance increases. That's why FET is a PTC device. Okay, if you take the like a pictorial representation, as temperature increases, definitely drain resistance increases guys. Yes. Similarly, what about transconductance GM? Guys, if current reduces, transconductance reduces na, because they are directly proportional, right? So guys, here let us take another color. Now guys, as temperature increases, the transconductance decreases, like this guys, GM. This is what the JFET parameters and the transconductance of FET. Got it? So guys, we will see in the next video. This is Shivram signing off. Jai Hind. Hi guys, welcome to SpaceGate Engineering Academy. Let us start a beautiful concept on FETs. What is FET? Field effect transistor. Guys, in this video we are going to discuss about JFET parameters, what are the parameters and what is the relationship among themselves, and the transconductance of FET. These topics are very, very important, crucial in FET's unit, and these are very important topics in terms of examination point of view. Remember guys. Now let's get started. Guys, JFET parameters. Usually the drain current of a FET is a function of VGS comma VDS. Yes, because guys, hope you know, from the drain characteristics, when you change the VDS, initially drain current increases and then becomes saturate. So the drain current is function of VDS only. Moreover, the peak value of the drain current is depends upon the VGS, because whenever VGS is 0, this is the maximum current, IDSS. Whenever you increase the VGS, the depletion region comes together so that the channel width, the conducting channel width reduces. As it reduces, the number of carriers move from source to drain decreases, ultimately current decreases. Hence guys, if it is VGS non-zero, then guys you will get some reduced current, you see here. Hence we conclude the drain current of a JFET is function of VGS voltage, VDS voltage. That's what we have written guys. See this like expression, if you explain, like for example y is equals to f of x comma w, just for example, let's assume like this, there is a function which is with respect, like which is expressed, which is depends upon x and w with two more parameters. How can you represent in Taylor series expression? If you take this expression and if you represent in terms of Taylor series expression and neglecting the higher order terms, we will get the expression as like guys ID by VGS into VGS, like you can take dou ID by dou VGS into dou VGS plus dou ID by dou VDS into dou VDS. Yes guys, of course there are some higher order terms also and we are neglecting them. So if you take this function and you express in Taylor series expression, you will get the equation like this guys, dou ID by dou VGS into dou VGS plus dou ID by dou VDS into dou VDS. Yes guys, when we assume the small signal operation, then definitely this dou ID can be considered as del, because guys we know del in the sense change, del ID by del VGS plus into del VGS. Similarly here also. Now guys, here what we can do is the same expression, this del ID by del VDS into del VDS, this one. See, as I said, it is a very small change, a small signal operation, where you can consider this ID, del ID as approximately ID only. You can consider as it is small signal operation. Yes. So guys, here if you take del ID as del ID, del VGS as VGS, del VDS as VDS, the expression can be written as ID is equals to ID by VGS into VGS plus ID by VDS into VDS. Yes guys, see this one, the del ID can be written as ID, similarly del VGS, del VDS. Now guys, here this is the expression. We know that is whenever you take the ratio, that means what about the current, how the current is changing at the output with respect to the changes in the input voltage. So it is always current by voltage is transconductance. Remember that transconductance, output is the current, input is the voltage, not at the same parameters like output current, output voltage, input current, input voltage. No, output current, input voltage is transconductance. So I repeat guys, whatever the term is present here is transconductance only, because it represents the ID, drain current, output current with respect to the input voltage VGS voltage, denoted by the letter GM, that is ID by VGS guys. Okay, remember. Similarly guys, here we have one more parameter called ID by VDS. Now it is ID, drain current, output current. VDS, output voltage, output side. Then output current by output voltage is output conductance, or else inverse of output resistance. Both are at the drain side, so it is a drain resistance. Hence guys, you can say drain resistance RD can be expressed as VDS by ID. Yes guys, we know like the transconductance units are ampere per volt because current by voltage, right, or mho or Siemens. This is what the point guys. Whereas drain resistance units ohms. Okay, so transconductance, drain resistance. Now guys, there is a new parameter called amplification factor. What is amplification factor? Mu. Okay, actually it represents the ratio of output voltage by input voltage. The basic definition is output voltage VDS by input voltage VGS. Now guys, the amplification factor, it is not mobility, remember, it is not mobility. Amplification factor mu, it is VDS by VGS. You take these two parameters and tell me how you get VDS by VGS. Do we need to multiply these two parameters or divide these two parameters or subtract or addition? It is simply multiplication guys. You take these two parameters guys, GM into RD, where GM is ID by VDS, RD GM by VGS, ID by VGS, RD VDS by ID. Now guys, ID gets cancelled, VDS by VGS, that's what here. So guys, here the relation between the amplification factor, drain resistance, transconductance is mu is equals to RDGM. This is a very important relationship in FET. There are three JFET parameters. They are mu, RD, GM, amplification factor, drain resistance, transconductance. Now guys, what are the units of GM? Ampere per volt, mho or Siemens. What are the units of drain resistance? Ohm. What are the units of amplification factor? Mu. No units because volt by volt, right? So remember guys, the mu is a dimensionless quantity, dimensionless parameter. Okay, remember guys, this is very important. These are the JFET parameters. So ultimately this expression can be written as, try to change the color because that is important, ID is equals to GM VGS, because guys in place of ID VGS we can write GM, right, and this can be written 1 by RD. So guys, here GM VGS plus ID by VDS can be written as 1 by RD, so that 1 by RD VDS. This is a very important equation for a drain current ID. I repeat guys, here the drain current equation of a JFET is GM VGS plus 1 by RD VDS. Now guys, with this expression you can develop the small signal model of JFET. Yes, coming to the small signal model of JFET, guys, by using this expression it can be represented as like this guys, where it is GM VGS and this one guys, this is 1 by RD. This is the one guys, VDS. Got it? So guys, the drain current is this ID. Hope you know this is gate, source, this is the drain, and this is the one guys. This is VGS, but it's a open circuit only guys because the gate current is 0. Between the gate and source there is a open circuit only, remember. This is the expression. Now you see this, you apply KCL at this node D, so that ID is equals to GMVGS current and this RD 1 by RD into VDS guys. You will get it. This is what the point guys. ID is equal to GMVGS plus 1 by RD VDS. Now the very important thing is, what is the difference between the H parameter model BJT, H parameter model, small signal model of FET? Guys, when you refer the BJT H parameter model, it contains 4 H parameters like this. Hope you know guys, there are 4 H parameters: HIE, HRE, VCE, HFE, IB, 1 by HOE. This is VCE and this is VBE, input, base, emitter, collector guys. This is the H parameter model of BJT, this is the H parameter model of JFET. Now guys, tell me what is the difference? The difference is, in JFET, in BJT, there is a connection from output to input. Connection in the sense there is a path, there is a connection, you can go, current can go, output can move from output to input, which is called feedback. Whereas, do we have here? In FET small signal model, is there a connection from output to input? No. Because guys, from here it can come, like how it will go, there is a open circuit now, from this to this. It is a open circuit only. Of course, the voltage across these 2 points is VGS, but it is a open circuit saying that IG is 0. In FET, the gate current is almost 0. So, open circuit. So, I can say that it's very important point, very important point. In JFET small signal model, there is no feedback connection from output to input. So, guys, if there is no feedback connection, what happens? If there is no feedback connection, you will get more gain, isn't it? Yes, as it provides a very high gain comparatively. Remember guys, JFET is a ideal amplifier compare with BJT. That's what the very interesting point. Note, JFET is a ideal amplifier over BJT amplifier or over BJT. Yes guys, this is what the importance with respect to the JFET parameters. Now guys, is it same for high frequency applications and all? No. Unfortunately guys, whatever I said, ideal amplifier and all is applicable to low frequency applications. This diagram is valid only at low frequency applications, whereas guys, if it is high frequency applications, then automatically guys there will be introduction of parasitic capacitances, internal capacitances. Here you get one internal capacitance, the capacitance between this drain and source, so CDS. There is a feedback, there is a connection, there is a capacitor present between gate and drain, CGD. there is a transition capacitance, internal capacitance between the gate and source, CGS. So guys, whatever the figure now is for high frequency applications. Now at high frequency applications there are internal capacitances, so there is a feedback even in JFET also. In this case, which amplifier is the ideal amplifier? Guys, in this case the ideal amplifier is BJT amplifier because its transconductance is higher than FET. So we repeat, at high frequency applications, as GM of FET greater than GM of BJT, we say ideal amplifier is BJT only, BJT amplifier only, not FET amplifier, because its transconductance is less. Whereas at low frequencies, guys, this is only the point. At low frequency applications, okay, at low frequency applications the JFET amplifier is only the ideal amplifier, okay.